No mai, haere mai. Welcome to this presentation. I'm Mark Apperley from the University of Waikato in New Zealand, and I'm going to be introducing a form of distributed generation node for the electricity grid that we've called GRID-LITE. This has been defined in the context of a single residential site, but it could easily be extended to a village or to a community. Its distinctive characteristic is that it supports rather than challenges network and capacity planning. To begin the discussion of the GRID-LITE concept, it's appropriate to look at the context in which this model arises. First, there is the growing awareness of climate change and the significance of greenhouse gas emissions, the approaching dilemma of peak oil, and the pursuit by many jurisdictions of energy independence. This, coupled with growing affordability and practicality of small-scale renewable generation, has led to an increasing number of people wanting to generate some of their own electricity needs based on a mix of environmental, idealistic, and financial grounds. A further recent background factor is a significant improvement in battery performance, together with production developments leading to lower costs. And to add to that, many of the moves to counter greenhouse gas emissions, for example in heating and transport, are themselves producing increased demands for electricity. This leads to the challenge of incorporating distributed renewable generation effectively in the electricity grid. Basically, it requires a different style of grid. The challenge is typified by what I refer to as the feed-in tariff dilemma. Small distributed producers expect to be able to export their surplus electricity, all that they can't consume locally, to the grid and be paid for it. But most of these renewable sources are unpredictable and can't be turned on or off at whim. Yet the grid still needs to be able to deliver the peak load required of it, so the growth of this distributed generation doesn't enable the reduction of the old installed capacity. And the only real gains or savings from the grid perspective are in reduced fuel consumption, not in capital investment. So as small-scale distributed generation becomes more widespread, the assumption that the grid will always be there as backup and storage becomes untenable. And we need to find a more symbiotic way of the grid and the distributed nodes working together. I'm reminded of a speech by John F. Kennedy, President of the United States back in the 1960s. With a small change, we can turn this into a succinct statement of our present problem. So what form does a GRID-LITE node take? It's based on an individual residential site with 5 key components. The first is a conventional household load or domestic load of appliances, lighting, heating and so forth, although a trending change is the addition of charging the family's electric car. It also includes a grid connection, working in both directions, but limited in some way, generally restricted to a maximum flow in either direction. That restriction might be contractual, or it may be physical or electrical, and imposed by circuit breakers. There will be local generation capability, probably in the form of solar PV panels, some battery storage, and importantly, a smart energy flow management system, which controls the distribution of the load between batteries, solar, and the grid, and channels excess generation back to the grid, all within the constraints of the grid connection. And as I suggested in my introduction, the concept and configuration could equally well be applied to a community grouping, like a village or a farm. There are a number of other models of distributed grid nodes which incorporate renewable generation and storage, so it's worth identifying the relationships between these and GRID-LITE. Let's start with off-grid systems, the extreme of the distributed configurations. Best characterized as an island, totally independent from the grid, so that all of its electricity needs are generated locally. But the drawback is that those needs cannot always be met sustainably, with backup generation most often powered by fossil fuels. The next model to consider is the grid-tied system, which has and is generally quite dependent on a connection to the grid, so it's better characterised as a peninsula. I include the net zero energy balance model here, since the form is identical. Net ZEB simply has a proviso that over a given period of time, normally defined as a year, the locally generated energy is equal to the locally consumed energy. But in order to achieve that, these configurations are also very dependent on the grid in the shorter term for backup supply and storage. This brings us to microgrid systems, which incorporate characteristics of both the off-grid and grid-tied configurations of the last two slides. For this reason, I describe them to be like an island connected to the mainland by a bridge. They're defined as being normally connected to the grid, but have resources such that they can survive independently when the need arises. So the bridge is really a drawbridge. How does GRID-LITE then compare with these concepts of off-grid, grid-tied, and net zero energy balance and microgrid? Well, like grid-tied, it's a peninsula, but one with a very narrow isthmus, the strip of land connecting it to the mainland, suggesting the more restricted grid connection. So how realistic is this notion of a restricted grid connection, and how could it affect our daily lives? Well, there are parts of Italy where individual households have limited connections, only 3 kilowatts, but they live with this, maybe not able to use the microwave while they iron their shirt, but that's not a disaster. California has progressive pricing tariffs, encouraging consumers to keep their demands low. And in some more remote rural areas of New Zealand, consumers pay a surcharge based on their highest annual peak 30 minutes. These measures have been largely motivated at limiting demand, so saving on capacity investment and or fuel costs, but they could equally well apply to controlling distribution capacity needs. And here we're talking about a limited connection with storage. How does this change things? Here's a very good example that's been around for 100 years or more. The standard flush toilet has storage and a utility connection limited to about 30 litres a minute. That's a 15mm water pipe. But when it discharges to flush the toilet, it delivers that stored water at more than 4 times the rate. Think of the savings in the capacity of the water distribution network. So the idea of local storage gives us load smoothing and the ability to deliver much larger bursts of power for a short period, much like the traditional flash on an old-fashioned camera, which used a capacitor to store electricity for rapid short bursts of power. So what benefits does the GRID-LITE concept bring? First, the distributed capacity makes a real contribution to the overall grid capacity. There are real reductions in peak loads because of the restricted grid connections, so it's not just the selfish cost saving for the individual. Second, it provides a much better basis for planning the new grid through reduced and known network demands, leading to more orderly planning for distribution and known requirements for isolated and distant consumers. Now, referring back to that diagram of GRID-LITE, a key component is obviously this smart energy flow management system. So what does it need to do? It has to understand the household needs and how different appliances or devices can be controlled, and the nature of the demands according to whether they're imperative, like making coffee, discretionary, like washing the dishes, or background loads, like a refrigerator. It needs to know what's going on externally, whether the grid is in surplus or in shortfall. And using this information, plus knowing the present solar output and battery state, and some knowledge of historical patterns, it optimises the energy flow between the load, the batteries, the solar panels, and the grid, taking full cognizance of the grid restrictions. Let's just take a quick picture of its operation. Here's a typical daily household load profile, power on the vertical axis and hour of the day horizontally, showing morning, midday and evening peaks and a late night low. And this is the output produced by a typical solar PV array, peaking around the middle of the day and producing nothing during the nighttime hours. If we combine these together, we see the periods, those above zero, when there is a demand on the grid, and the period in the middle of the day, below zero, when the house would be in surplus and wanting to store energy back to the grid. But with GRID-LITE, we have grid flow constraints. Let's suppose our maximum draw is 800 watts, and our maximum upload or feed-in is, say, 600 watts. To meet those constraints, the system needs to draw energy from the batteries when the download constraint is exceeded, or perhaps defer some of the load if there's not enough energy available in the batteries. And when the upload or feed-in constraint is exceeded, it needs to store the excess in the batteries, or initiate some discretionary load, maybe one previously deferred, and of course it may channel energy into the batteries at any other time it seems necessary, so long as the operating point remains between the constraints. To better understand some of the issues around any of the distributed generation models we've discussed, and to see their relationships, I'm going to define what I refer to as the interval energy balance space. These are the 5 components of GRID-LITE, and indeed any of those distributed models. We're going to look at the energy flows between them, and we'll assume that the energy flow management system is in charge and is the distribution point, or hub. So there's potentially flow to and from the grid, all channeled through the energy flow management system hub. The household load represents an outflow from the hub, and the PV array an inflow to the hub. If the battery flow, however, is represented here as 2 separate components, an outflow from the hub representing charging of the batteries, and an inflow to the hub representing the drawing of energy from the batteries. For the purposes of this discussion, those 2 outflows from the hub, which are internal to the site, so they don't include grid flow, are added together as the total household energy consumption. And those 2 internal flows to the hub are added together as the total household energy production. This separation of battery charge and discharge is counterintuitive in comparison with other models, but vital if we're to consider behaviour over short time periods. It allows us to define our interval energy balance space, with the vertical axis representing total generation and the horizontal axis representing total consumption, as described a moment ago. In this space, a diagonal represents those points where the generation exactly matches demand over whatever time period is being considered. And for example, this point represents a situation where generation has exceeded demand over that interval. If we're talking about GRID-LITE, we can also plot grid constraints in this space: the maximum export or feed-in, and the maximum import or load. The operating region for our GRID-LITE system can be characterized by this shaded area. Now suppose the load and generation at a particular time would have the system operating in region A, outside of the operating region. Here the load exceeds supply, and to fix this we can either reduce the load or increase battery contribution, effectively increasing the total household generation, or possibly we could use a combination of both measures. If the load and generation combination led to an operation in region B, where production exceeds the load, we can correct this by increasing the load, or by reducing production, or again by a combination of both. We're now going to look at some real data in this space, data that represents a real household load over a full year measured at hourly intervals, combined with actual solar PV data over the same year at the same location. The solar panels have been sized to give net zero energy balance, so their output over the year is equal to the total annual household load. That gives us a 4 kilowatt panel. And the battery capacity has been set to the average daily load, 16 kilowatt hours. The net ZEB model has been analysed with and without storage. That makes little difference to the annual balance, but a big difference to the balance over shorter intervals. And arbitrary grid flow limits have been set for the GRID-LITE scenario. The smart energy flow management system we've used for this analysis is far from smart. There is no demand-side management implemented at this stage. and no smart battery charging algorithm. The battery efficiency has been set at 85%, a figure based on experience. That's the amount of energy delivered to the batteries which can be retrieved. This first example describes a basic grid-tied scenario without any storage. The dots represent the hourly balance, so there are 8,760 of them. This vertical column represents an excess of generation, obviously during the daytime when the sun is shining and the household load is not high. And this dense set of dots forming a horizontal line shows load without any generation, the nighttime situation. If we add storage with exactly the same load and generation, we get this representation of a net zero energy balance scenario. This strong diagonal line, containing the majority of the 8,760 dots, shows that even without smart energy management, at an hourly interval, balance is achieved most of the time. Although clearly the batteries are not always able to satisfy the nighttime load, and there are occasions during the day when the batteries are full and cannot divert the solar output, so the grid is used as storage. For the GRID-LITE scenario, again with the same load and generation data, it can be seen that over hourly intervals the operating region is achieved much of the time. And it's interesting to see the extent to which the operating point sits on the boundaries. As with the previous examples, there are a significant number of hours when the batteries are full and fail to consume the solar output, so that the grid feed limit is exceeded. In reality, some sort of failure would occur. Just for comparison, this graph shows the off-grid scenario, where by definition the generation must always match the load. In reality, of course, it may not be able to, so some of the points higher along the diagonal are likely to represent system failures. It's also interesting to observe what happens when we increase the analysis interval to 24 hours. Now we have just 365 dots on the graph. And in this case of the grid-tied scenario with no storage, we see the averaging has reduced the dispersion of the data points, although this column suggests that there is less variation in the daily load, that's the horizontal, than there is in the daily solar output, that's the vertical. On this daily average basis, the situation with storage shows less off-axis deviation, with balance achieved most days, although it is still dependent on the grid to bring those other points into line when averaged over a year. On a daily basis, the GRID-LITE scenario is very successful, with the operating region achieved 100% of the time. Although to be effective, this needs to be achieved at every instant, the fact that daily balance is very achievable suggests that with good demand-side load management, instantaneous balance is also a realistic goal. Just to show the utility of this interval energy balance space, I also have graphs here showing the annual balance. These have just one data point, representing that annual total. For the situation with no storage, we get perfect balance because we calculated the required solar PV capacity to achieve this. And of course, the cost of this balance is total dependence on the grid for storage and backup generation during the year. With storage, the scenario we've referred to as net zero energy balance, a perfect annual balance is not quite achieved because the batteries are operating only at 85% efficiency. We could easily resize the solar panels to correct this, but we should also note that this scenario too is dependent on the grid for storage and backup. A similar slight annual out of balance also shows up with the GRID-LITE scenario, and again, resizing the solar PV could fix this. You may have noticed that the annual totals here are lower than the net zero energy balance totals, 7,200 kilowatt hours instead of 9,600. And this can be attributed to an unwise battery strategy in our analysis, which meant that the solar capacity was not fully utilised. Battery full situations occurred more frequently with GRID-LITE than with net ZEB. So to summarise, I've introduced the GRID-LITE concept and compared it with other distributed generation node models, specifically off-grid, grid-tied, net zero energy balance, and microgrid. I've also introduced the interval energy balance space as a means of comparing these different situations meaningfully, particularly when we're looking for grid balance and symbiosis. The model is the subject of ongoing research. In particular, we're looking at appropriate sizing techniques for the critical parameters such as grid constraints, PV capacity, and battery size. And through measurement and simulation, we're exploring the impact of grid flow limitations and load management strategies on both the delivery of the goals and on comfort, quality of life, and convenience. We're also planning to develop a large-scale simulation to observe the consequences of adoption of the approach at local and national levels. Thank you for viewing this presentation. I must acknowledge the contributions of my two graduate students, Paul Monagatti and Joris Suppers, who provided the annual data sets for the analysis, the hourly household data and the PV data respectively. Should you want to find out more about our work, then contact details for our Energy Informatics Research Group are at the URL shown on this slide. Thank you again. Kia ora mai.